Hello students, Dr. Church continuing to look at some energy applications. Yesterday we looked at potential energy due to gravitational fields or gravitational potential energy, which is an energy of position. And before that we looked at kinetic energy, which is the energy of motion. So the formula is there, kinetic energy 1/2 mv squared, potential energy gravitational mgh. And so we see a connection there when we talked about the roller coaster problem. If we ever think about that, remember you get pulled up to the top. We'll say that you started at 0. Of course, it's still moving at the top, so it's not exactly 0, but let's just simplify it. If the velocity, initial velocity was 0, and you dropped it 25 meters, and then it came out of the hole for about 5 meters, and ended up with a 20-meter height differential, what would the final velocity be? And so this seems to be a difficult problem at first, but if we know that the initial energy potential is mgh, and we know that if we let this be just the differential there, then we know that the final velocity could be calculated where that energy lost is gained in motion, mv squared. And if we set those two things equal, we would actually see that the mass cancels out, and we know h is 25. We know g is 9.81 times 25. So difficult to write with the mouse. And then we could solve for v, right, when we set those two things equal, and that's a fairly simple solution there, and we could calculate that. Now we know that this path really doesn't matter. We could take a different path and still end up here, and that's what we see here. Here's a toy car. A spring launches the car with some initial velocity, which is not 0, but the car still ends up here. And interestingly, assuming a frictionless path, right, conservative forces, conservation of energy, it wouldn't matter if the car went this way or this way. That final velocity would be the same, because the energy input into the system here is equal to the energy output to the system here, and so that final velocity would end up the same. So that's the physics behind that is something you definitely need to know. Well, gravitational potential energy is not the only way to store energy, an energy of position. If you've ever worked with a spring or a guitar string, anything that's elastic in nature, a rubber band, we can actually store energy in it. It's stored into the molecular bonds of that material. And based on the design of the spring or the rubber band, how big is it? How thick is it? How stiff is it? What material is it made from? What is the temperature of it at a particular point in time? It will change what's called the spring constant, which tells you how stiff that spring is or how much force it takes to compress it or to stretch it. And so when we do compress it or stretch it, it stores energy at its what's called its free length, right? No forces are involved, so there's no energy stored in it. It's just sitting at rest, basically. But as soon as we apply a force and we compress it, then that spring is pushing back. So its molecular bonds have stored that energy, and it wants to release it and give it back and go back to an equilibrium point. It's like a marble that's wanting to track to its lowest point, or water wanting to go to its lowest energy state. Well, that spring wants to go back to its lowest energy state and release the energy that it's holding. And so it's potential energy, right? It can be used. And so we can solve some problems with springs as well. So potential energy is stored in a spring is determined by the average force required to compress it. And then that's captured in that K, which is the spring constant. So force, this is an important equation here. So the force to compress or stretch a spring is the spring constant times the distance, right, that we stretch it or compress it. And if we plotted that, right? The force versus compression or distance, right? And we then calculated the area under the curve. That would be the work done. So remember that work is F delta X, right? And that's just this times that, which is the work under the area under the curve graphically, which is the work or the energy. Remember, work and energy are synonymous. And so that would be the energy of the spring. And for a spring constant, we see that the more we compress it, the area goes up linearly. It's not this. It's not a straight line, a horizontal, right? The force required to compress the spring actually goes up. In other words, the further you compress it, the harder it gets to continue to compress it. And so that is a linearly demonstrated, but with an increasing value, right? And so the area under the curve is just the area of a triangle. So it's 1/2 BH squared, or in this case, 1/2 KX squared, right? And so that's the energy stored in a spring. Now you'll sometimes see that written like this, okay? So elastic potential energy of a spring displaced a distance X. And so U as potential energy, U sub S is 1/2 K spring constant times distance X squared. And so there's another formula you'll need to know. It's probably, I'm sure it's on your equation sheet. So a couple quick checks here on potential energy. 3 balls are thrown from a cliff with the same speed, but at different angles. Which has the greatest speed before it hits the ground? So they all start here and they all end here. So would this one, or this one, A, B, or C have a greater speed? Well, you might think that this one has to go higher, so it would be maybe moving faster when it got to the bottom. This one dropped. It didn't have as much time to get there. So you might think that there's a difference there, but when we think of this in terms of potential energy, right? And this potential energy, mgh, converted to kinetic energy, 1/2 mv squared, right? Well, if those are equal and h is constant, then the final velocity would be constant. So they in fact would have the same speed when they got to the bottom. And here's another one. A hockey puck is sliding, so a frictionless surface here at 4 meters per second. It has to climb to the top of this hill. So as it goes up, what's going to happen to its energy? Its potential energy is dropping. We're taking energy out of the system. We're doing work as we lift the puck. As the puck is lifted, the energy in the system drops. So will it have enough energy to actually get up here to the top? Well, you can't just guess at that one, right? You can't just look at it and guess. Oh, well, I think that's going fast enough. You're going to need to do a little calculation. So what is it? Well, you've got mgh is the potential energy that's necessary, that's going to have to come out of it, right? You have to give it that much potential energy, all right? It's 1/2 mv squared. So the velocity is 4 meters per second. So if we put that in there and square it, that goes away, right? So does this quantity, is it enough to overcome this quantity? So 9.8 times 1, right? So does that work out? Well, let's see. It requires v squared equal 2gh, right? So remember, this drops out. Solve for v, right? So we've got multiply both sides by 2, by 2. Take the square root of vgh. Y is 1 in this case. So it needs to have the square root of this, right, velocity, and that's not going to make it, right? So the v squared, the v is not sufficient to get it up to the top. Another little quick example here of elastic energy potential, right? Achilles tendon stretches when you run. It stores energy. You probably don't realize that happens so quickly. And so here's the extension in centimeters of your Achilles tendon. Here's the resisting force. Achilles tendons are very strong, as a matter of fact. And what energy is stored in this system? Well, we would need to calculate the spring constant and multiply that by the displacement of the tendon, which is just acting like a spring, right? So we go back to the slide. Let's find the slope of this. The spring constant is actually, remember that F, right, force is equal to Kx. Okay, so just remember that force is being plotted on the y-axis. So this is your y-axis. This is your x-axis. So what is this? This is just y equals mx plus b. In this case, b, the y-intercept is 0. So we just want to find the slope. What's the slope of the line? Well, in this case, the slope is actually, right, the spring constant, k. And so this is just, remember, F. So hard to make an F with the mouse. Kx, right? So that's the slope of the line. So that's what we're calculating here. We calculate the force divided by that stretch, and then that gives us a quantity, right, in newtons per meter, and that's the spring constant. And that makes sense if it's force per unit stretch. So it's force newtons per unit stretch, meters, right? And that gives us a number there. And so when we solve for that and plug that back into the energy potential, right, then we have, just plug and chug that in, 2.1 joules of energy stored. So that's not a tremendous amount of energy in there for each little flexion, but there you go. But it does add up over a long run, as you runners know. Now we're going to go and talk just for a second about thermal energy so we can look at conservation of energy. But I'm going to go ahead and do that in a separate video because these tend to get a little tedious. So we'll look at thermal energy and conservation of energy next.